Of the series of photomicroscopes that Carl Zeiss designed and built during the middle of the last century, the model illustrated above is the first type and is often referred to as the Zeiss Photomic 1. The essential difference between this microscope and most of the others of the day was that the Photomic had an inbuilt 35mm camera system, as well as being provided with a complex prismatic light pathway. It is a large microscope by most standards and weighs in at around 42 pounds or 19 kilograms, excluding accessories such as the heavy 5 by 4-inch camera ensemble. It probably wouldn't win a gold medal for elegance or style, but as a flexible workhorse with some reservations, it most certainly would. The innards of this rather large stand are complex to say the least, and the diagram below shows the basic optical and mechanical internal layout. There are also minor differences among the various models.
The photomicroscope makes observing of specimens a lot easier. It produces photographs of specimens. The photomicroscope is not that different from the ordinary microscope that we are very familiar with. The only component that a photomicroscope has is a camera that produces digital image which can be used for processing, analyzing, and presenting images of specimens obtained from the microscope. Such processing is now commonplace in a number of diverse fields, such as medicine, biological research, cancer research, drug testing, and many more.
Scanning objective. This shortest objective is useful for getting an overview of the slide, especially handy with some of the slides that contain whole organs like a section of the spinal cord, lungs, respiratory tract, and ovary.
Low power objectives. This next shortest objective is probably the most useful lens for viewing slides. Almost any feature you need to observe in this course can be located with the 100 times total magnification this objective provides. As an added benefit, the low power objective is always safe to use as it cannot be lowered to the point of contacting and thus possible breaking a sight. This is also true of scanning objectives.
High power objective. This objective, sometimes called the high-dry objective, is useful for observing fine details such as the striation in skeletal muscle, the arrangement of conversion system in compact bone, types of nerve cell in the retina.
Oil immersion objective, also known as OIO. This longest objective is used for observing the detail of individual cells, such as white blood cells and cells involved in spermatogenesis. The lens must be used with a special formulated oil that creates a bridge between the tip of the objective and the overslit.
In science, many useful devices are made, such as microscopes and telescopes. Use more than one lens to form an images. To analyze any system with more than one lens, work in steps. Each lens takes an object and creates an image. The original object is the object for the first lens, and that creates an image. That image is the object for the second lens, and so on. A basic microscope is made up of two converging lenses. One reason for using two lenses rather than just one is that it's easier to get higher magnification. If you want an overall magnification of 35, for instance, You can use one lens to magnify by a factor of 5 and the second by a factor of 7. This is generally easier to do than to get a magnification by a 35 out of a single lens. A microscope arrangement is shown in the picture along with a ray diagram showing how the first lens create a real image. This image is the object for the second lens, and the image created by the second lens is the one you've seen when you look throughout the microscope.